So, ladies and gentlemen, now let's have a look at the last stage of the rasterization-based rendering pipeline, the so-called fragment stage. So let us first briefly summarize the result of the vertex stage, or the vertex shader stage. We sometimes call it the vertex shader stage because we can write a shader program that controls the operation that are performed on the vertices in that stage. So we have said that every vertex is transformed via the model view transformation and then via the perspective projection transformation. And this gives a vertex coordinate, a four-component vertex coordinate with a fourth homogeneous coordinate that can be or is usually not equal to not equal to 1 anymore. And we have also looked at how the normals are transformed that are issued per vertex. For them, we cannot use the model view transformation directly, but we have to use the transpose of the inverse of that model view transformation. Yeah, and we have said that additional attributes like color and texture coordinates are just passed through that stage, so they remain unchanged. Yeah, so here's the different pipeline stages again, with the vertex shader stage in green. Green means that we can program this stage, and then the transformed vertices are passed on to the rasterization stage, and the rasterizer then performs a couple of operations like the perspective division and another transformation, the viewport transformation. We haven't yet talked about that transformation, but we'll do in a second. And finally then comes, so to say, the core of the rasterization process. The rasterizer then computes the coverage of the projected triangles in the pixel raster, and for each covered pixel, a so-called fragment is generated. Yeah, let us look first in a little more detail at what the rasterizer does. Now we have said that the transformed and attributed vertex stream is passed to the rasterizer stage. Attributed means that for each transformed vertex we still have a color, a texture coordinate, a normal, whatever attribute we have specified. And then the rasterizer, we have said, cannot be controlled via a program as the vertex shader or the fragment shader stage can be, but the rasterizer can be configured. For instance, we can configure the rasterizer in such a way that it performs backface culling and view frustum culling. So what is backface culling? We have already talked about this, that every triangle that has a face pointing away from the camera is just culled, is, so to say, taken out of the pipeline so that it does not is not passed further into the upcoming stages. And view frustum culling means that whatever is not entirely inside the view frustum is also removed from the pipeline. Yeah, then the rasterizer performs the final division by the fourth homogeneous coordinate of each vertex. And by doing this, the rasterizer computes the projected x, y, and z coordinates. And in particular, it is worth noting here that the rasterizer does not throw away the z coordinate, but keeps that value because this value will be needed later on in order to determine which of the fragments, if multiple fall into the same pixel, are actually taken because they are closest to the view plane. Yeah, we have said that then after the perspective division, the vertices are then in the -1 to 1 normalized device coordinate space. And then comes the final viewport transformation, which computes the coordinate of the pixel into which the vertex is projected. So each vertex is falling into let's say a coordinate in the NDC, in the normalized device coordinate system. But because the rasterizer wants to compute the coverage in the pixel raster, the rasterizer first determines into which pixel each vertex is falling, and then using this information for the triangle that is going to be processed, the coverage in pixel space can be determined. Yeah, then for each of these triangles, the rasterizer determines the pixels that are covered by this triangle, and for each such pixel, a so-called fragment is generated. These fragments are then further passed into the upcoming fragment processing stage. And per vertex attributes, like color, like texture coordinates, like normal values, these are just interpolated to the fragments via barycentric interpolation. So the rasterizer, as you see, the rasterizer performs the interpolation of the per vertex attributes to the points on a triangle that are seen through the pixels in the screen for you. So in fact, we will see the fragments actually correspond to the points on a triangle that are seen through a certain pixel. And we have seen already when talking from a conceptual point of view about the rendering process, there we saw that in order now to determine the color of a pixel, we need to know what is the color at the point of a triangle that is seen through that pixel. And we have said that since the attributes are only issued per vertex, we need to interpolate these values from the vertices to the triangle points. Yeah, and also, as we will see, because we typically perform the illumination by using the Phong illumination model at the fragments, we also need to interpolate the normal vectors, which are given only at the vertices, and then they are smoothly interpolated to all the triangle points which are seen through the pixels, which are in fact the fragments, so that then every fragment has an interpolated normal vector. And by means of this normal vector, or by using this normal vector, then in the fragment processing stage, you can compute the illumination. Yeah, but first of all, let's look at the viewport transformation. Now we have said after the perspective division, all the vertices have been transformed to the normalized device coordinate space. So all the coordinates are in the range from -1 to 1. So all vertices that are visible, that are in the view frustum, have a value ranging from -1 to 1. If a vertex is outside that interval in any of the coordinate components x, y, z, then that vertex is not inside the visible view frustum. So now we want to map or transform these NDC coordinates to pixel coordinates. And first of all, let us briefly talk about what that means and why we do that. So let us assume you want to render your final image on a pixel raster comprised of 1024 times 512 pixels. And that then means that, for instance, if after the perspective division by the rasterizer, a result comes out as here. So the x and the y coordinate of the transformed vertex are 0.2 in NDC coordinate space, and the z coordinate is equal to 0 in NDC coordinate space. And then you want to map this NDC coordinate to the window coordinate space, which is now going from 0 to 1023 and 0 to 512 in y. And this mapping, which performs that transformation, is called the viewport transformation. So here you have the normalized device coordinate space ranging from -1 to 1 in each dimension. And then if you have, for instance, a projected coordinate here, then you want to map that coordinate now to the corresponding location in the window coordinate space, where it now gets assigned a pixel coordinate or a pixel integer index. So the only thing the only difference in the transformation is what we see here. So you see that the z coordinate after the perspective division, that is not transformed to a pixel coordinate, but rather that z-coordinate is mapped from -1 to 1 in NDC coordinates to 0 to 1 in viewport coordinates. No, that's the only difference. So we handle the z-coordinate here differently than the x and the y-coordinate. Okay, so and now let's look at how the transformation looks like, which performs that thing. Well, here you see it is a transformation that is essentially comprised of 3 separate transformations. Now, the first thing you do, you scale the coordinates by a constant scaling factor of 0.1 along either axis. No? And because in normalized device coordinates, the coordinates range from -1 to 1, after scaling, no? The coordinates in the visible range from -0.5 to 0.5. Then comes the transformation which translates all the coordinates by 0.5 in each dimension. No, that means that the coordinates which are now from -0.5 to 0.5 after the first transformation are now translated so that they come to lie from 0 to 1. And now that you have everything from 0 to 1, you perform the last transformation, and you see now this is just a scaling by px and py. These are the x and z, is the x and z or the size of the viewport along the x and the y axis, meaning that you now scale everything from 0 to 1 to 0 to px minus 1 along x and 0 to px minus 1 along the y coordinate. And you see that we have a 1 here, meaning that the z value now remains unchanged, so that after the transformation the z values are just ranging from 0 to 1. So yeah, that is the viewport transformation, which now gives for every vertex a pixel coordinate, and keeps the z value of that vertex now as a scalar value between 0 and 1. Yeah, and now comes the rasterization stage with the projected vertex coordinates. You can now think about rasterization as a purely 2D problem, because all the vertices have now been projected into the pixel space. Every vertex has a pixel coordinate, also a depth coordinate, but in order to determine the coverage of pixels in the pixel raster by the triangles, you don't need the depth coordinate. And then the rasterizer, by whatever method, simply determines for every triangle which are the pixels that are covered by that triangle. Here the rasterizer, for instance, just tests the pixel centers. So if a pixel center is inside a projected triangle, then that pixel is covered. If that pixel center is outside, then the pixel is classified as not being covered. And you see that, or no, you don't see this, but the color indicates this. For every pixel in the pixel raster that is covered by any of the triangles, a so-called fragment is generated. You can really think about a fragment being associated to a pixel, and the fragment, as we will see, is essentially corresponding to the triangle point that is seen through that pixel that is covered by the triangle. So, yeah, so you see here in this example, for instance, for the right-hand triangle, the rasterizer would generate 1, 2, 3, 4, 5, 6, 7, 8, 9 fragments. And for the left-hand side triangle, the rasterizer would compute 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 fragments. You see that, of course, depending on the size of the triangle and under which angle you're looking at the triangle and how far it is away from the view plane, different numbers of fragments are generated for each of the triangles. Yeah, and now if you link this image here to the image we were discussing when I introduced the rendering process. We were talking about that kind of pixel raster and the pixel centers, and that we want to determine what is seen through the pixel centers. Then you can probably now imagine what these fragments are. The fragments which are generated are now corresponding to the triangle points that are seen through the pixel centers. Yeah? And now the rasterizer does what we have also done already, by hand, so to say, for each fragment that is now generated for one of the covered pixels. The per vertex attributes, like the color, like the normal, also the Z value that is also interpreted as a per vertex attribute here, or the texture coordinate, they are interpolated to these fragments. So again, all the information is sitting at the vertices. We have now determined, or the rasterizer has now determined, all the pixels which are covered by the projected triangles. The rasterizer then determines what is the triangle point that is seen through the pixel centers of the covered pixels. And then to each of these points, the rasterizer interpolates all the per vertex attributes via a smooth barycentric interpolation, similar to what you see here. And what does the rasterizer interpolate here? The rasterizer essentially interpolates whatever you have specified as per vertex attributes. If you have specified colors, the color will be interpolated. If you have specified normals, the normals will be interpolated. If you have specified texture coordinates per vertex, then the texture coordinates will be interpolated. Only the Z value, you don't have to specify explicitly. The Z value comes out of the, first of all, of the vertex shader stage, where the transformation of the vertices is performed. And then the rasterizer, by doing the division by the homogeneous coordinate W, and then doing the viewport transformation, keeps that Z value, and then interprets the Z value as any other per vertex attributes, and interpolates the Z value also across the triangle to the fragments. And why this is necessary, we will see in a second. Just keep in mind for now that for every fragment which is generated here, for every fragment, not only the color, normal, texture coordinates, etc., are kept or interpolated, but also for that fragment we have an interpolated Z value, meaning that by means of that Z value we can know what the distance of that fragment, or more precisely, what the distance of the point that is seen through that pixel here on the triangle is to the view plane. And we will see later on how we use that information in order to do occlusion culling. So summarizing that, the result of the rasterization stage is then a set of one fragment for every pixel that is covered by any of the triangles that have been projected. And each fragment stores its, so to say, pixel coordinate. So each fragment is assigned to a certain pixel in the pixel raster. Let's call this coordinate the xy, integer coordinates, xy integer coordinates. And every fragment also has an interpolated Z value, an interpolated color value, a normal value, a texture coordinate value, etc., whatever you have specified per vertex. And now you see essentially, by looking at the information that is stored for every fragment, so we know where this fragment is located in the pixel raster, we know its Z value, so we know how far it is from the image plane, and this is essentially the information we would need in order to, from this information we can now exactly tell where in the global world coordinate space the point that is seen through that pixel is located. If I give you the pixel raster and I tell you exactly what the camera parameters are, so what the size of the view plane is, what the distance of the view plane is, the near and the far values, and then I tell you there's a pixel, and through that pixel you look at a point in a distance z from the screen space. Then you can immediately tell me what the the world space coordinate of that point is, because you know under which transformations the point has been projected, and you would just have to invert these transformations in order to get the initial location in world space from which that projected point came. And that means that a fragment, in fact, is a surface point seen through the respective pixel.